We could go through and write electron configurations for each atom, but we get a lot of the same information by only talking about the valence electrons using Lewis dot structures. For example, a hydrogen atom is found in group 1, so it only has one electron, which we can draw on the side of the hydrogen's chemical symbol H. This single electron in the Lewis structure gives us some idea of how hydrogen will interact with other atoms by two rules. 1. Electrons like to come in pairs, so any single electron is likely to form a bond. The number of single electrons generally matches the number of bonds. And 2. Atoms always want to fill their shell. The shells of each period are different, so the first shell only has an s orbital, and there's a 2-electron max. Hydrogen, therefore, can only form one bond in most cases. We can also fill out the Lewis dot structures fairly easily for pretty much any atom. We only need to find the number of s and p electrons for that atom. So for boron, since it has two s electrons and a p electron, which we can see from its position in the periodic table, it will have 3 electrons. We place those electrons around boron, one on each of 3 sides. Doesn't matter which sides. And can see that boron likes to have 3 bonds when neutral, one using each of its unpaired electrons. We can also see that boron can easily accommodate another bond and still be within the 8-electron max for atoms that have s and p orbitals available to them. Carbon is just 1 over, so it will have 4 electrons. We draw that in the Lewis structure as 1 up, 1 right, 1 down, and 1 left. Carbon, therefore, has 4 unpaired electrons and therefore likes to have 4 bonds. But because there's no space left over, it will already have 8 electrons. It cannot accept any more once it has the 4 that it wants. Once we move on to nitrogen, we have an extra electron once we've put 1 on each side, so we begin to pair electrons. Again, where we put the pair doesn't really matter. This tells us that nitrogen, having 3 unpaired electrons, likes to have 3 bonds. We can also see that there's a pair of electrons that's left over, unbonded, that could be shared with something else without breaking nitrogen's octet. For oxygen and fluorine, make sure that you can actually determine what the Lewis dot structure would look like as well. Notice that oxygen will tend to have 2 bonds from the 2 unpaired electrons, but it could still share electrons from a lone pair. Similarly, fluorine tends to have 1 bond, but could, in theory, share electrons from any of its lone pairs as well. Within a group, the valence structure will stay the same, so sulfur's valence shell looks exactly the same as oxygen's, and chlorines are the same as fluorine. What does change is the ability to use d orbitals in bonding. So sulfur and chlorine can actually accommodate up to 18 electrons, which is why some of the ions you might already know, like sulfate and perchlorate, have more than 4 bonds. The Lewis dot structures can tell us about how many bonds are likely to exist for an atom. These bonds are generally covalent. They share electrons. Each bond contains 2 electrons, generally 1 from each atom. Atoms can also double or triple bond, which doubles or triples the number of electrons that are between the atoms, a double bond having 4 electrons and a triple bond having 6 electrons. Atoms can also quadruple or quintuple bond, but those bonds don't typically involve carbon, so that's really just a teaser for all that you could learn in an organic chemistry course. Anytime we have atoms interacting, we can draw their Lewis structures by arranging the atoms and either placing the dots representing bonding electrons between the atoms, or by replacing every 2 electrons in a bond with a line instead, representing those 2 electrons. The negatively charged electrons between positively charged nuclei are not static. The bonds are constantly being stretched and compacted. Push the atoms too close together, and they can't account for the repelling between the positively charged nuclei. Stretch the bond too far apart, and the electrons aren't sufficient to hold the nuclei together. The height of the hill shown with a soccer ball, or the energy that it takes to separate the atoms, is called the bond dissociation energy. We call the distance between atoms that gives the lowest bond energy the bond length, even though the bond length is usually changing back and forth. The bond length is really just the lowest energy point, or the average distance as a molecule vibrates different bond lengths. It's often useful to think of our bonds as springs. The length of the bond is always changing, like if the soccer ball was rolling back and forth between the 2 slopes. Drawing a Lewis structure for the H2 molecule is fairly simple, but every other possible molecule is more difficult. so it's helpful to have a systematic way of drawing Lewis structures. You've done this before in general chemistry, but I want to remind you of these steps before we move into organic chemistry. We'll also talk about some shortcuts, but you'll always remember shortcuts better if you're able to return to the fundamentals. The first step in drawing a Lewis structure is figuring out how many electrons total that we can use for the structure. Remember that only valence electrons are likely to be bound, so we can simply look at the Roman numeral group number on the periodic table to figure out how many electrons there are. Or we can count the number of atoms we are from the left side of the periodic table using the S and P blocks only. Or if you can identify the number of dots in a Lewis structure, but you can't remember exactly how you do it, it's the same number. So if you can figure out that, you can figure out how many electrons there are for the valence structure. After we figure out the number of valence electrons for each atom in a molecule, all we need to do is add them together to find out how many valence electrons there are in the entire molecule. When we have an ion instead of a molecule, we need to add an electron for each negative charge, remembering that electrons are negative, so anions, negatively charged ions, always will have more electrons for more negative charge. For a cation, on the other hand, we need to subtract an electron for each positive charge. We can use sulfuric acid, H2SO4, as an example for how we do this calculation. The hydrogens each have one valence electron, the sulfur has 6, and the 4 oxygens all have 6, for a total of 32 electrons. The next step in drawing a Lewis structure is to write down the arrangement of atoms and draw single bonds between all connected atoms. In many cases, you might be given a formula. Most chemists write the formulas in a way that give hints to the connectivity. Any hydrogen at the beginning of the formula is acidic and is typically attached on the outside atom. The first atom that isn't hydrogen is at the center of the molecule, with atoms that follow typically connected to the center molecule. For example, H2SO4, sulfuric acid, has 2 hydrogens at the beginning, indicating that they are acidic and attached to an outside atom. The next atom given is sulfur, which means that that's at the center. We'll place the 4 oxygens around the sulfur, and then we're going to add the 2 hydrogens to any of the outside atoms, usually an oxygen if available. If the atoms are the same, it doesn't matter where the hydrogen is attached at all. It's common to just write the hydrogen next to an atom to which it's bonded to clean up the structure a little bit. So here we have OH written instead of an O with a bond drawn to an H. It still implies the bond. As a general rule, the central atom is usually a non-hydrogen atom with the smallest electronegativity, meaning you are more likely to have an atom as central as you move down the periodic table and left in the periodic table. So since sulfur is below oxygen, we could also assume that it's at the center because it's less electronegative. After we have the basic structure down, we have to make sure that we have the right number of electrons. We calculated 32 electrons in step 1, but now we've added 4 bonds between sulfur and oxygen, and 2 bonds between oxygen and hydrogen, 1 for each OH, for a total of 6 bonds. Since each bond is 2 electrons, we've used up 12 electrons already, and we have 20 left to place. It's usually easiest to start on the outside and work in, so we'll start with each oxygen. We need to remember that every oxygen will want to have 8 electrons, including the bonds. For the oxygens bonded to both the sulfur and hydrogen, we already have 4 electrons already, 2 from each bond. We only add 2 lone pairs for each of these. On the other oxygens, we add 3 lone pairs for a total of 6 electrons. Combined with the total of the 2 electrons to the bond, we'll have 8 electrons in each of those. Notice that by filling up the oxygen's orbitals, we've used up all 20 of the remaining electrons. In this case, it doesn't matter because the sulfur already has an octet from the 4 single bonds. The structure shown is already a correct Lewis structure. If the sulfur did not have an octet, we would need to move one of the pairs of electrons from an oxygen on the outside into a bond with sulfur, which would allow us to maintain the octet of the oxygens while also increasing the number of bonds to sulfur. Again, we don't need to do this for the molecule shown to get a valence Lewis structure, but we actually can because sulfur can exceed the 8 electrons by accepting electrons into an empty d orbital. The structure shown below has lone pairs from 2 of the oxygens moved into double bonds with oxygen. the oxygens here still have their octets, and the Lewis structure shown on the bottom is actually also valid. Notice that when we made this structure, we moved electrons from the O's and not the OH's, so that every oxygen has 2 bonds. Similarly, we moved a pair of each of the 2 oxygens electrons rather than moving 2 pairs from a single oxygen and forming a triple bond. The structure with 2 double bonds is actually the best structure for this molecule, which we'll see later on in the chapter when we talk about formal charges. Now we can have a chance to work through some examples. I put an abridged version of the steps we just talked about at the top of the slide as a reminder. Our first example on the left is N2, nitrogen. We start by finding how many electrons we have to work from. Each nitrogen brings 5 valence electrons, so we only have 10 electrons. We draw out the 2 nitrogen atoms with a line between, accounting for the 2 electrons. We have 8 electrons remaining, and we'd add 6 of those 8 remaining electrons to one nitrogen to fill its octet, and we'd add the other 2 to the other side. This gives us 10 electrons, so we can't actually add any more. However, the nitrogen on the right doesn't have an octet yet, so it needs to have at least a double bond to increase towards an octet. We can move electrons from the leftmost nitrogen into a double bond to increase the number of electrons available to the rightmost nitrogen. However, when we do this, this still leaves the rightmost nitrogen with only 6 electrons, so we need to move another 2 electrons into an extra bond, now giving a triple bond. Once we have a triple bond, we have an octet for each nitrogen and a valid Lewis structure. Hooray! Working through the next example, we have dinitrogen monoxide. Each nitrogen gives 5 valence electrons and oxygen gives 6. So we're at a target of 16 valence electrons for the whole molecule. When we draw out the atoms, nitrogen is the first thing listed that isn't a hydrogen, so that goes at the center, with the other nitrogen and the oxygen connected to that central nitrogen. Another way of looking at it is that the nitrogen is less electronegative than the oxygen, so that's going to go at the center. We attach the atoms with single bonds, which use up 4 of our electrons, and we have 12 of those 16 left. I'm going to put all 12 electrons on the outside atoms to begin with. That gives me octets on each side, but it leaves only 4 electrons on the center nitrogen. We need 2 more pairs of electrons, so either a double bond from each side, or a triple bond from the left side, or a triple bond from the right side. While all those structures are valid, putting a triple bond between the 2 nitrogens actually leads to the best structure because the formal charges on the atoms, which are actually shown in this molecule, are the lowest. Take a moment and try to work through the other examples shown to make sure that you understand how to create a Lewis structure. Now, check your work against the answers given. If you've got one wrong and can't figure out why, reach out to me for help and we'll work through it together. There are a few types of molecules that tend to work a little differently. Anything with an odd number of electrons is always going to be missing an octet on some atom. There's no way to get an octet on every atom. Anything with boron tends to be shown with only 3 bonds and only 6 electrons. The reality of boron compounds is more complex, but at this stage, we just draw the Lewis structure with only 6 electrons. It's a lot simpler. And as we've already indicated, anything in the 3rd period and beyond can actually accept additional electrons, although they don't need it in every case. So on the bottom, you see another example of an expanded octet, something with more than 8 electrons. It's good to be able to draw Lewis structures from scratch, but as you start to get used to drawing Lewis structures, you might notice some patterns emerging. The simplest pattern is that every atom tends to have the number of bonds indicated by unpaired electrons in its Lewis dot structure. Hydrogen has 1 unpaired electron and tends to make 1 bond. Boron has 3 unpaired electrons and tends to make 3 bonds, and the trend continues. This is always true as long as you don't have charges on the atoms, and as long as you don't have d orbital contributions from the atoms. If the atom is charged, a negative charge will generally result in 1 fewer bonds. You can see this in the table in the difference between nitrogen's 3 bonds and N-'s 2 bonds, or the difference between oxygen's 2 bonds and O-'s 1 bond. For a positive charge, the atoms typically have extra bonds. Nitrogen plus has 4 bonds instead of 3 with a neutral nitrogen. Oxygen plus has 3 bonds instead of the 2 with a neutral oxygen. Carbon, an exception, actually goes down to 3 bonds when it gets a positive charge. And it's different because with carbon, you're losing your octet at the same time. Once you get used to seeing these, this often can make drawing a Lewis structure much easier and much faster. To use an example from before, I know right away for N2O that if I have a nitrogen on the outside of a molecule, it probably wants to be triple bonded if it's going to be uncharged. I also know that if I have a triple bond to the nitrogen, I can only have a single bond to the oxygen without exceeding the nitrogen octet. That would give me 4 bonds to nitrogen on the center, and therefore a positive charge, and then 1 bond to the oxygen on the right, and a negative charge. These shortcuts make the most sense the more problems you do. You'll be able to see the patterns more clearly. Don't try to memorize straight towards a shortcut. You'll lose out. You won't be able to remember and you won't be able to apply it correctly. Instead, as you do problems, try to recognize these patterns in the structures that you draw. If you approach problems that way, you'll learn the shortcuts without trying and on a much better and more retainable foundation.
Generally, the buildup of charge is less stable than having a neutral atom. Formal charge is an important way of accounting for electrons in a given structure to see if that structure is stable. Formal charge is always a comparison between the expected value, how many electrons each atom brings to the molecule, and how many actually end up on an atom or ion. Notice that when we count electrons in a bond, we divide them equally between the atoms participating in that bond. Take this example for hydrogen fluoride. On a hydrogen, there are no non-bonding electrons. We'd expect 1 electron from H, and we get 1 from the bond, so the formal charge ends up being 0. Likewise, fluorine should have 7 electrons. We get 1 from the bond and 6 from the non-bonding electrons, and it has 7, and we end up with a formal charge of 0. Let's work through an example of drawing a molecule from a structure and then assigning formal charges on that Lewis structure. First, we're going to start out by drawing a Lewis structure. We have 3 nitrogens. We know that one of them has to be central, and we know that each of those nitrogens is going to bring 5 electrons, and we'll get 1 extra electron from the negative charge. We know that we have 16 total electrons, so we'll start out drawing those 3 atoms and single bonds in between them. That accounts for 4 of our electrons. We have 12 left. We're going to add 6 to each of the outside nitrogens, and that's going to give us 16 total electrons. That gives us the right number of electrons, but notice that the central nitrogen does not have an octet. So we need to move some of the outside electrons into double bonds. We're going to move outside electrons into double or triple bonds to fill the central octet. Notice in the molecule that I've drawn, I moved 1 set of electrons from the left nitrogen to a double bond and 1 from the right to a double bond. This is the Lewis structure that we'll assign formal charges to. When we assign formal charges, we notice that the nitrogen on the left has 4 electrons that are not bound, and we get 2 electrons from the double bonds, 1 from each bond. And so we take 5 minus 6 and we end up with a negative 1. The nitrogen in the center has 1 electron from each of the 4 bonds, and so we take 5 minus 4 and we end up with a positive 1. And the nitrogen on the right is exactly the same as the nitrogen on the left. Formal charges really can be a great way to assess how good a Lewis structure is at representing reality. Generally, the things that represent reality the best are the things that have the lowest overall formal charges. So compare this azide molecule to these other 2 Lewis structures that we could have drawn for the azide molecule. Both of those structures have the same number of total electrons, but they have a much higher formal charge on one of the nitrogens. And so whilst that each of those structures will contribute some of the character of the molecule, they're less accurate at representing what's really happening in the structure. Once you've been doing formal charges for a while, you might realize that atoms usually have a few different formal charges available to them, and that they are always associated with bonding patterns. For example, carbon normally has 4 bonds. As long as it has 4 bonds, it will always have a formal charge of 0. If it has 3 bonds and a lone pair, it will always have a formal charge of -1. And if it has 3 bonds with no lone pair, it will always have a formal charge of +1. Notice that in this example, where carbon is positively charged, there are only 6 electrons. There are very few examples where we don't have a full octet, one of them being a carbocation, a positively charged carbon, another being boron, and the last being hydrogen as H+, where it doesn't have its full duet. And these are exceptions rather than the rules. Now notice with this carbon, that's a carbocation, the positively charged carbon, that carbon is unstable because of the charge. It's also unstable because it doesn't have a full octet. Notice that for all of the other atoms that have full octets, as we move electrons from bonds to lone pairs, the formal charge becomes increasingly negative. So we have 4 bonds here on nitrogen. As we move some of those electrons into a lone pair instead, as a neutrally charged nitrogen, the formal charge is now neutral. And when we have just 2 bonds on nitrogen here, and then 2 lone pairs, we end up with a negative charge. A similar trend is observed with oxygen, positive with 3 bonds, neutral with 2 bonds, and negative with 1 bond. That's generally true. You move more electrons into lone pairs, you end up with a more negative formal charge.
So let's practice some. Pause the video and try to identify the formal charge for every atom. Each hydrogen on every one of these molecules is bound only once. Since hydrogen has 1 valence electron normally, and it gets 1 electron from every bond, in every instance it has the same number of electrons that we'd expect. The 1 from its valence minus the 1 from its bond gives it a formal charge of 0 in every instance shown. This is generally true. It's really rare for hydrogen to carry a formal charge. Carbon also has the same number of electrons that we'd expect in each case shown. Each carbon normally has 4 valence electrons, and in every case that's matched by 1 electron from each of 4 bonds. So 4 valence electrons minus the 4 electrons from the bonds gives us a 0 formal charge in each of the molecules shown. This is also the norm. Carbon with a formal charge is also really rare. For each of the oxygens shown, they are also neutral in each case. Each has 4 electrons all to itself as lone pairs, and 1 electron from each of the 2 bonds for a total of 6 electrons. That matches its 6 valence electrons. So 6 valence electrons minus 6 electrons from lone pairs and bonds gives a formal charge of 0. Oxygen, nitrogen, and elements after the second period tend to be more likely to form formal charges, even though oxygen does not in either of these cases. So for every atom shown, the formal charge is 0. This is good because formal charges that are closer to 0 tend to indicate more stable Lewis structures, which means that we've probably done these Lewis structures correctly.
We know that to draw the best Lewis structures, we need to minimize formal charges on as many atoms as possible. However, in some cases, there is no difference in formal charge between possible Lewis structures. The 2 structures shown below are both correct Lewis structures for formate, CHO2-. Both have the same accumulation of formal charge. In actuality, they are both right. If we look at a charge density map of formate, as we see below, we can see that the negative charge, the red parts, are distributed evenly between the 2 carbons. The 2 structures of formate are its resonance structures, structures that can show only part of the reality of the molecule. The true molecule looks like a resonance hybrid, a combination of all possible resonance structures. Resonance structures occur whenever there are 2 or more valid Lewis structures, but never are the actual molecular structure, whereas the resonance hybrid is the true structure. Notice how the resonance hybrid has partial negative charge that's equally distributed between the 2 oxygens, just like the electron potential map. The resonance hybrid is always a combination of the resonance structure that is weighted based on their stability. The most stable resonance structures contribute the most. If resonance structures are equally stable, they contribute equally, which is the case here. They are equivalent. Inequivalent structures contribute unequally, but we need to be able to assess the stability of resonance structures to be able to tell this. In order to stabilize a structure, two things can happen. The most important factor for stability is full valence shells. The next most important factor is to have low formal charges. It is essential to remember these two factors because they will help us to understand many of the reactions we encounter in chemistry. Look at the structures of acetyl chloride shown above. Take a moment and assign formal charges to the oxygens and chlorines. Write this down and bring it to class. On the left structure, all the formal charges are 0. On the right structure, oxygen has a -1 formal charge and chlorine has a +1 formal charge. Because the resonance structure on the right has formal charges, it contributes far less to the overall resonance hybrid. However, it still contributes some. The chlorine will have less electron density in this molecule than we see in many others without such resonance structures. Because no atom truly holds a full negative charge in a resonance hybrid, resonance is an incredibly stabilizing factor. The extra electrons are stabilized by delocalization, meaning they spread out to reduce charge in any one place. This is always stabilizing compared to concentrated localized charge. Resonance stabilization is most large when there is significant contribution from more species. This happens when there are many places to localize charge, and when the contributors have similar energy. The more resonance structures, the more stable a molecule is in most cases.